next question is, where do we get energy from? I want you to think about that. Where do we actually get energy from? I want you to pause this video and take 1 minute to write down all the places we get energy from. Okay? So go ahead, pause now. All right, so you should have been able, especially after doing the reading last night, you should have been able to come up with lots of places that we get energy from. We get energy from the sun. We get energy from the potential energy of water in waves and in reservoirs and hydrothermal energy. We get energy from, we said directly from the sun and thermal. We get energy from coal, from oil, from nuclear power, right? We get energy from all of these places. Okay. Now, one of the things that we want to be able to recognize is, what is the difference between a primary energy source and a secondary energy source? Okay. So there's two sets of definitions that I want you to be able to get here. The first one is primary versus secondary. Primary is a source that has not been transformed or converted before use by the consumer. Okay. So what's an example of a primary energy source? Well, a primary energy source would be, for example, if you are using solar heating, not photovoltaic cells, not solar cells, okay? But if you're using like mirrors to directly focus the heat of the sun to heat something up, to focus on a pan, that would be primary energy. If you have a water tank up on the surface of your building so that the sun shines on the water tank and that heats up the water that you're going to use in the house, that is a primary source of energy. If you have a sailboat and you are using the wind directly to push your boat, that is a primary energy source. It's a source that hasn't been transformed or converted before you use it. Okay? You could also consider primary source as a fossil fuel if you're talking about heat, right? You use a fossil fuel and you burn it to get heat. Therefore, a fossil fuel is a primary energy source of heat, right? So these are all primary sources. Now, on the other end, we then have secondary. Okay, a secondary energy source is one that results from transformation of a primary source. For example, electricity. You get electricity from several different ways, right? Nuclear power, right? Nuclear power, you don't use the energy directly from the radioactive nuclear power, right? You take that, you turn it into heat, which then does several other things, turns a turbine, right? You have all these things that happen, and eventually it's turned into electricity, and then you use the electricity. The electricity is a secondary source, okay? Batteries, right? You use batteries all the time, like those size D, size C, AA batteries, the battery in your car. Those are all secondary sources because that energy has come from somewhere else, and it's being turned into that source that you can then use later, okay? Primary sources are always great because then you're being as efficient as possible. Because of the second law of thermodynamics, every time you go from one energy source to another, you are losing energy, right? Energy is being lost. That was one of the pieces of the second law of thermodynamics. You can't take energy and turn it completely into work. So anytime you change from one source to another, well, you are losing energy, okay? You're being less efficient. Okay, so that's one set of definitions there. The other one that we want to talk about is renewable versus non-renewable. All right, so we're talking about renewable resources. What is the definition? Well, when we talk about renewable resources, okay, usually what we're talking about is we are talking about resources that can be replenished in your lifetime. That is renewable. Right? I mean, you could say, well, coal is renewable. You just have to kill a bunch of animals, put them down in the planet, and leave them there for 1 million years, and then it's renewed. Okay, well, congratulations, Einstein. But yes, that's not how we define renewable resources. Renewable resources have to be able to be renewed within your lifetime. So non-renewable are like nuclear fuels, right? You can't renew that within your lifetime. Fossil fuels, right? Getting the chemical potential from those fossil fuels, oil, carbon, coal, natural gas, all those things are things that cannot be replaced within our lifetime. Okay, we just use them up and that's it. Renewable resources are things like solar power. Obviously, we continue to get solar power from the sun. Water, like getting water from waves or using it from a reservoir that goes down a mountain and turns turbines. That is renewable because that water will come back because of the water cycle. Geothermal energy, biomass. Biomass is an interesting one because people say, well, how is that renewable if I'm burning a tree? Well, the reality is you can replant that tree, and with 100 years, within your lifetime, 70 years, that tree will grow back. So that is considered renewable because it's renewable within your lifetime. Okay? Awesome. So I think that's the big idea here, and I think we're ready to move on to the next one. So here's something to consider. Generally, biomass is considered better than fossil fuels, okay, like oil, coal, natural gas. I want you to think about why biomass is considered better than coal, oil, and natural gas. I want you to remember that in both of these situations, you are burning something and you are putting carbon dioxide into the atmosphere. So why is biomass better? Okay, go ahead and pause it, and then I'll give you an answer. Pause now. All right, so hopefully you've taken time and you've written down a couple of answers. I'm sorry you don't have a neighbor. If you want to talk about it with somebody, call them on the phone. That's fine. See if you can come up with some ideas together. But if you did it on your own, I hope you did it as well. So here's a couple of things that I came up with. Maybe you came up with some other things. The first one, of course, is the obvious one because of the previous slide. Biomass is renewable, right? You burn a tree, you can replant it in 70 years or even less, depending on the type of tree and how big it is. Your tree is back. It can be renewed over and over and over again. That's one reason why it would be better. Okay. A second reason is this. Where does the tree actually come from? The physical material that tree is made of. Where did that come from? Well, the reality is that most of that tree is made up of carbon dioxide. Carbon dioxide and water is what makes up that tree. And if you think of the molecules that are in a hydrocarbon, for those that are in chemistry, it's carbon, hydrogen, and oxygen for the most part. You have some other things in there, but that's mostly what your tree is made of, carbon, hydrogen, and oxygen. Hydrogen is the smallest of those atoms, so really is the least important. The carbon and the oxygen are the most important part, and that comes from the carbon dioxide. Okay, so why is biomass more important or better? Well, think about this. The carbon dioxide that you get when you burn that tree, well, that tree took that out of the atmosphere. And so that is carbon dioxide that recently was in the atmosphere and was taken out. Okay, so that can be within kind of a contained cycle. You plant a new tree, it's going to take that carbon dioxide right out of the atmosphere again. You burn it, puts that same carbon dioxide back. And so it's basically a cycle, right? You grow a tree, the tree takes the carbon dioxide in, you burn it, and then the carbon dioxide goes back out. But then you do the same thing, right? You make a new tree, and it takes that same carbon dioxide and pulls it back in until you burn it, and then puts the carbon dioxide back out. So like I say, it's a cycle. It's the same carbon dioxide that's being put back into the atmosphere and then breathed and then taken out. Okay? The difference is that the oil, coal, and natural gas all have carbon dioxide that was taken out of the atmosphere millions of years ago, right? So that carbon dioxide has not been in the atmosphere. It was not there 10 years ago, right? The tree didn't use that. The coal didn't use that to make it. It's been out of the atmosphere for a long time. And so when you burn that oil, coal, and natural gas, it's putting carbon dioxide back into the atmosphere that hasn't been there for millions of years. And so it's actually increasing the total amount of carbon dioxide there. Now, why do we care about carbon dioxide? Well, we'll talk more about that, but not today. That's going to come up maybe 3 lessons down the line. So probably next week we'll talk a little bit about why we care about carbon dioxide and what the big deal is and why it's so important that we not put so much extra carbon dioxide into the atmosphere. All right? Yeah, let's move on. You saw this in your textbook. I believe this is the image that was there. A couple of things just to be aware of. BTU, for some reason, is used when talking about energy. It's unlikely that you'll have to deal directly with BTUs, but it's historical. It's one of those English unit systems. A BTU is ridiculous. 1 BTU is the amount of energy required to raise 1 pound of water 1 degree Fahrenheit. That's what a BTU is. Okay, kind of like a joule, right? A joule is the amount of energy required to raise 1 kilogram of water 1 degree Celsius. This is the English system equivalent. But it's really, I mean, they use it, but we aren't really going to have to worry about that. Just, I want you to recognize how big, how big a BTU is. It's somewhat similar to a joule, but within a degree of confidence. So the other thing is TOE. TOE. TOE represents tons of oil equivalent. Or in other words, the amount of energy that you get by burning 1 ton of oil. Okay? So that's a lot of energy, right? You can see how 500 quadrillion BTUs is only 12,000 megatons, okay? Or 12 I guess that's about 12 billion toes. Okay, so there's a significant difference. Just be aware these are the types of units. You really shouldn't have to deal with these. You should be more comfortable with your SI units. Okay, but we're just I really just have it there so you can see we're talking about a lot of energy here. All right. Let's see. I want to add. I want to show you another graph. So here's your thing. 1 BTU is about 1 kilojoule. 1 TOE is about 42 gigajoules. All right. So there's a little bit of conversion for you there. Okay. I want to show you this graph. I want you to look at these 2 graphs. Notice that some of the things are similar. You've got coal, which is black for both of them. Natural gas, which is orange. The hydro, you've got the hydro, which is getting energy from, waves and dams and things like that. That's different here. This is liquids. By liquids, it means like oil, okay, which is brown over in the other one. So I want you to look at these 2 graphs for a second. I'm going to ask you to pause it, and I want you to think about the difference in these 2 graphs and why there's a difference, okay? Because here I see that hydro is 16.3%. I see that nuclear is 10%, right? I see that oil is only 4.4%, okay? That was in 2013. The one over here is 2010. Do you really think that big of a change happened between 2010 and 2013? What's going on here? What's the difference in these 2 graphs? Go ahead and consider that. Pause the video now. All right, so hopefully you had a chance to look at that. I like to present this just because it gets you used to looking at graphs and paying attention to details in graphs. All right, now the detail that I want you to pay attention to here is the fact that the left-hand side is all energy use, the world marketed energy use. So that includes all the stuff used to make electricity. It includes the cars, everything that you're getting energy from, right? This one over here on the right is only electricity generation, all right? Now, the big one, of course, was the oil. Here you've got oil at 35%, and over here you had oil at 4%. Well, that's because oil isn't generally used to make electricity, right? Oil is used in your cars and your airplanes and all those other things. So here in the U.S., lawnmowers and all those things is what the oil goes to. And so these two graphs are significantly different, but it's because they're demonstrating two different things: electricity versus overall energy. But what I do want you to notice is that regardless, only about 16% of our energy comes from nuclear and renewables, what we would consider to be clean sources, right? Over here, you've got about 26%. Maybe if you count these other renewables, you're up to maybe about 30% of electricity comes from what we would consider to be clean sources. All right? So I think we're ready. Let's move on. I'm almost done with this one. All right? I want you to look at this one. You have a table with specific energy and energy density. Okay, you should have read about these last night. If you did, I would like for you to take 2 minutes right now to pause the video and write down a definition for those two and see how well you do. All right, ready, go. All right, so hopefully you did pause it. If you didn't, shame on you. I know I can't see you, but that doesn't mean that you shouldn't do what you should do, which is to try to spout out what information is stuck in your head here. All right, so let's go ahead. Specific energy and energy density. So specific energy, we've kind of talked about before. Remember, specific, the word specific means per kilogram, right? So this is just the energy per kilogram. So 1 kilogram of wood gives you 16 megajoules of energy. So how much energy do you get per kilogram of that? Okay, so looking, you'll notice that wood is 16. Coal can be anywhere from 20 to 60, depends on how pure it is. Gas and natural gas are a little bit better. We'll talk about that a little bit in our next video and talk about why possibly natural gas is a little bit better. And then you've got nuclear power, which obviously puts out a whole lot of energy. Fission and fusion. Fusion putting out almost 10 times as much energy than fission. And then you've got hydroelectric power, which you don't get a lot of energy, but you got a lot of water there that, of course, can continue to be used. So that's specific energy. Energy density is talking about per volume, right? Usually when you talk about density, you're talking about mass per volume. But this is energy density, so it's the energy per volume. So if I have 1 meter cubed of this material, how much energy am I going to get out of that? Okay, so you can see, again, different levels of those. You've got wood, which has a fairly low energy density. You've got your fossil fuels, which are slightly better. And then you've got your nuclear fuels, which have a huge amount of energy for a very small volume. And then you've got your hydroelectric power right here. So my question for you is this: why are fossil fuels so popular if nuclear fuels have 10 times as much energy in them? Why? Well, the reality is, number one, it's easier to get. Number two, it's easier to control. And number three, people aren't scared of it. That's the reality. If you can get past that, if you can deal with the difficulty of getting it and containing it, and if you can deal with the fact that people are scared of nuclear energy, you can actually make a heck of a lot more energy with a lot less materials. I mean, look at this, from 10 to the 6th power up to 10 to the 15th, right? That's like 10 billion times more energy in nuclear fuel. Okay, it requires much less, puts a lot less into the atmosphere, and yet because of this fear we have of nuclear energy, it doesn't get used as often. All right. Keep in mind, why do we care about specific energy density? Well, larger energy density means that it's cheaper to transport stuff, right? One of the problems with natural gas is it's not very dense, right? Natural gas has a higher specific energy, But because it's gas, it's not very dense, and so therefore when I'm transporting it, I might need 100 times as many trucks in order to transport that energy, right? So these are kind of ideas that we want you to be able to kind of think about and look at and understand what these numbers are kind of trying to tell us.